All right. We are live for day 8 or part 8 of the Synacor challenge. Um, and where are we? So when we left off, we added some instruction modeling, started extracting functions and digging through those, and we found the Ackermann function being called. This one right here. Um, and we didn't actually give it the correct input that would make the Ackermann return at the right time. But we did figure out how to skip past that. So we bypassed that, and that allowed us to find a new area. And while we were there, we found a journal, and that's where we left off, with that journal as a cliffhanger. So what I think I want to do today is revisit this area. So we can start off by going off to that journal and learning about what it is we were going to have to be doing next. And I think this time we'll work through, I want to add inject a few more hooks so that when register 8 comes up in other places, we get a notification that it's come up. And we get the address of the function that was called, and then we can extract that and see if that tells us any more. I don't think we need to know much more. Ice Cold Witch, hello. And then at some point we'll have to actually reverse the Ackermann function. Where's the actual implementation? I'll leave this bookmarked here. Yeah, I'll leave that up there for later because we'll be coming back to the Ackermann function. So let's do our wish list. Let's see. So tonight we're gonna add hooks for R8 access. See whenever that's read or written to. Probably not written to, but certainly, anytime it's read or there's arithmetic done with it, we'll want to know. And then let's see. Oh, right. We want to read the journal, and scout ahead in the new area. I'll probably have to revisit that area once we actually reverse engineer the Ackermann function. Figure out correct R8 value for Ackermann. That we still haven't done yet. And my understanding of that is that until that is fixed, we'll still end up in the right place. Oh, where did I put that gist? We'll still end up in the right place. We'll just have weird behavior. Let me see my gists up here. The strange book. Okay. Determine the value of the 8th register, which would have been accepted by the confirmation. So we set the register to that value, activate the teleporter, and bypass. If it's set correctly, no anomalies should be experienced, but if it is set incorrectly, the mechanism will not protect us. So I don't know what it's protecting us from, but we'll find out. We'll find out. So figure out why we need that confirmation mechanism. So with that, let us jump into Synacor. So we're going to go into our VM state and let's add in those hooks. So an obvious one, I suppose set here. Set register, what? Set register A to the value of B. Oh, these aren't registered in doc comments when you put the angle brackets. So I suppose if argb is R8, we'll want to do a little print line here. So if b equals regref or arg.ref, and then reg.r8. So we'll want something like R8 R8 has been read, and then we want the address. So we'll want something like pc.address.hex. Okay. And I suppose we'll also want that if R8 gets set explicitly, though I don't think that should happen. Anything else we might want? Let's say, I don't know. I don't think we'll be pushing it. Maybe if any instruction. Let's do this. Let's take the instruction. We'll turn it to string instead. That way we can just catch all of them. So def check R8. So there's an instruction, and this will just return an instruction. Or we can do a tap actually. So this can be a unit, and we won't use that. We'll use instead inst.show. And if inst.show dot contains R8. Yeah, exactly. Well, kind of exactly that. Then we'll print line R8 accessed and then the address. That should do us. Okay. And then import util.chaining. Now we can just tap instruction with that. So .tap check R8. Cool. I think that works. With that, oh, this show needs something. We need a given instance of Synacor.memory. Was it not needed anywhere else? Okay, well, just using memory then. And registers. Oh, they're in like opposite order or something. Okay. That'll do us. Let's just compile. And let's get that a run. R8 accessed. Wait, when? Why? It was accessed that early? Okay, that's interesting. That's already interesting. So we'll have to check that line. So we are at ruins with a teleporter. So let's use that teleporter. Oh, no, not yet, not yet. Let's set the value of R8 to something. So set R8 to 142. And then let's use a teleporter. Am I missing something? Okay, great. So R8 was accessed here, here. Oh, and there was a read. That's redundant. We didn't need that second line there. But at least we know what kind of access it was. Let's comment this out. Or I don't know, just delete that. And you know what? Actually, before we go on, I think I'd actually like to show not just the address, but let's just show the whole instruction. So val int string. So we'll do that. And then this whole thing can be int string. And then we put it in here as well, int string. Okay, so let's exit and let's do that again. Okay, so there's a jump true. So if it's 0, it skips altogether. Okay, so set R8 to 42, and then we'll use a teleporter. All right, so we skipped past that, and then we set R1 to the value of R8. So it is going to be read into register 1, and then something gets done with it. And that's probably like the actual verification. Okay, so a strange electronic voice is projected into your mind. You wake up on a beach with a slight headache. It begins to rain. The message fades away. This is a sandy beach in a cove on some tropical island. It is raining. The ocean is to your south, and heavy foliage is to the north, and the beach extends east. The beach extends west and east. So what I wanted to do this time around was draw an actual map as we're going. So we have our starting location. I think I'll use green. We're not too greened out, are we? So here's the start. It's the beach. We can go east and west. Let's start east, and we know it's more beach. And from here we can go north. And if we go back south, okay, so we can go, what did we go? East first. So we can go east, and then north, and then back south. Let's go west from here. Okay, that's back at the start, west. And from here we can go east or north. So let's try north. Large trees, there's a steep rock face to your west blocking your path, but we can still go east. We can't go east any further. Is this? Hold on. I think we've been here. Have we been here? Okay, so this goes all the way across, actually. If you go back west, just confirming. Okay, south, east, and let's go north from here and see where we end up. And from here, we can go west. So actually, let me just redraw this. Yeah. So there are two spots here. Both of these go north to the same spot. South goes that way. So that's just one way. And am I getting this right? I don't think it matters too much. Okay, so we're currently here. Let's go north. And from here, we can't go east or west. And it's sounding like it's a triangle. So if you go, oh, so here's like the true north path. And this north just joins into that. Okay. So that's our opening. Nothing to miss there. Um, you know what? I think I want more room because we'll be going north quite a ways. All right, so we have our start. We have east, west. We have north. Um, we have north here. And there we go. So that's our beginning of the map. Oh no, Bad Corp is doing Synacor and Bash right now? That's amazing. We finally bullied her into it. So let's go north. Did they just start now? Or did she just start now? You're on a narrow path between two steep rock faces, which look like they have been here for thousands of years. Rain tickles down through the vegetation and moss, and through the leaves, you can occasionally see a sliver of light hundreds of feet above where the rock walls end. Okay, and there's more to the north. So let's keep going. And it's another north-south with the sign Treasure Vault Access. You just saw the stream was running. Cool, cool. Do you know if Dave Eddy streamed tonight? Because I'd like to see him finish. Okay, so up to another north-south, and there's a sign here. I know we can draw a little sign. And north goes to you stand at the entrance to a natural cave. You didn't see a stream from Dave? Fair enough. Um, it is a busy season. But he's in Bad Cops chat. Cool, cool. You stand at the entrance to a natural cave, which looks like it hasn't been visited in quite some time. Light pours in through the opening to the south, while fireflies light the path further into the cave to the north. Okay, so let's go north into the cave then. So we ended up here. There's another path north. We are now in a cave, and there's another path north. The cave is a little wider here. You find a cobweb-encrusted remains of a small camp. Although you don't suspect the broken pieces of the tables and chairs will prove useful to your guests, the fireflies seem to like using the debris as a shelter. A passageway leads north and south, and there's an alcove in the east. Okay, so this is the alcove where we ended last time. So we'll mark this as the alcove with a journal. Just type a J there. All right. So from here, let's go east, and let's actually read that journal. So we'll take journal. We'll read journal. Or no, I guess we look at the journal. All right. Day 1, we have reached what seems to be the final series. The final. Scroll up there. Day 1, we have reached what seems to be the final in a series of puzzles guarding an ancient treasure. I suspect most adventurers give up long before this point, but we're so close. We must press on. We are so close. Just until 5 a.m. and we're good, right? P.S. It's a good thing the island is tropical. We should have food for weeks. Day 2. Xena, hello. The vault appears to be sealed by a mysterious force. The door won't budge an inch. We don't have the resources to blow it open, and I wouldn't risk damaging the contents even if we did. We'll have to figure out the lock mechanism. Okay. Vault, lock. The door to the vault has a number carved in it. Each room leading up to the vault has more numbers or symbols embedded in mosaic in the floors. Okay. We even found a strange glass orb in the antechamber on a pedestal itself labeled with a number. What could they mean? So everything's labeled with numbers. So there's some sort of puzzle having to do with the decorations around here. Um, we finally built up the courage to touch the strange orb in the antechamber. Oh, where were we? To touch the strange orb in the antechamber. It flashes colors as we carry it from room to room, and sometimes a symbol in the room flashes colors as well. It simply evaporates if we try to leave with it, but another appears on the pedestal in the antechamber shortly thereafter. It also seems to do this even when we return with it to the antechamber from other rooms. It evaporates when you return to the antechamber. Okay, so it vanishes. I guess you have to visit the rooms in a certain order, maybe? When the orb is carried to the vault door, the numbers on the door flash black, and then the orb evaporates. Did we do something wrong? Doesn't the door like us? We also found a small hourglass near the door, endlessly running. Is it waiting for something? Is that like the Ackermann check or something? No, that wouldn't make sense. That's just for the teleporter. That's a teleporter's check mechanism. Um, some of my crews swear the orb actually gets heavier or lighter as they walk around with it. Is that even possible? They say if they walk through certain rooms repeatedly, they feel it getting lighter and lighter, but it eventually just evaporates and a new one appears as usual. Okay. So as you walk through rooms, it gets lighter and lighter and then evaporates, but can get heavier too. So it depends on the room. So it has like a stat that gets modified as you move around until it disappears. It doesn't like being carried out, and if I'm reading this right, if you bring it back to the antechamber, it will also evaporate. I'm not sure. Day 21. 21. Big leap. Now I can feel the orb changing weight as I walk around. Depends on the area. The change is very subtle in some places, but certainly more noticeable in others, especially when I walk into a room with a large number or out of a room marked star. Ooh, so like it's multiplying? So is it adding the numbers in the room and then multiplying by some constant if there's that? Perhaps we can actually control the weight of this mysterious orb. Okay. Day 34. Oh, wait. These are Fibonacci days. Day 1, day 1. 1, 1, 2, 3, 5, 8, 13, 21, 34. Okay, that's a hint. Interesting. Now I can feel the orb changing weight as I walk around. Oh wait, no, crew members. One of the crew members was wandering the rooms today and claimed that the numbers on the door flashed white as he approached. He said the door still didn't open, but he noticed that the hourglass had run out and flashed black. Okay. When he went to check on it, it was still running like it always does. Perhaps he's going mad? If not, which do we need to appease, the door or the hourglass? Both? Interesting. Yeah, I don't know if that's an Easter egg or a hint, but we're on to day 1555. The fireflies are getting suspicious. One of them looked at me funny today and then flew off. Uh, okay. I think I saw another one blinking a little faster than usual. Or was it a little slower? We're getting better at controlling the weight of the orb, and we think that that's what the numbers are all about. The orb starts at the weight labeled on the pedestal and goes down as we leave a room marked minus, up as we leave a room marked plus, and up even more as we leave a room marked a star. So every time you leave a room, that's when it changes. Entering rooms with larger numbers has a greater effect. Okay, so if you leave a room marked plus, you're gonna add whatever is the number is of the next room, is what it sounds like. Day 89. Every once in a great while, one of the crew members has the same story. That the door flashes white. The hourglass has already run out. It flashes black, and the orb evaporates. Are we too slow? We can't seem to find a way to make the orb's weight match what the door wants before the hourglass runs out. If only we could find a shorter route through the rooms. Okay, so we'll probably have to make a map of rooms. And we could probably do a search for this in code to map up our route. Yeah, because it seems like you have to get a certain sum at the minimum time. Day 144. On an earlier stream, he asked Eric about Easter eggs not found on the main path, and he said, of course. Yeah, I'm sure it's packed with Easter eggs. I bet even in the bytecode, there's stuff untouched that is Easter eggs, and you'd have to like properly decompile it to find it. I don't know. Maybe like afterwards, if I want to find the Easter eggs, I could do a memory log of everything that's accessed and see what isn't accessed. Day 144, we are abandoning the mission. None of us can work out the solution to the puzzle. I will leave this journal here to help future adventurers, though I'm not sure what help it will give. Good luck. Alrighty. Well, we have to check out these rooms then. So let's look. Where are we? So we're in the alcove. We can go west back onto the north-south trail. And let's go north. Okay, the tunnel slopes deeper underground to the north, but the fireflies are all around the light to your path. Actually, give me just a second here. I need to check something. Okay. And let's get back to it. So this tunnel slopes deeper underground to the north, but the fireflies, yeah. And here is the vault antechamber. So we can call it VA. There's a big 22. Actually, we'll just label it a 22. So there's a 22. And this contains the orb. And there's a north, east, and south. Okay. North, east, south. There's no west. I'd like to give east a shot first. Vault lock. You're in a grid of rooms that controls the door to the vault. The floor of this room is a large mosaic depicting a minus symbol. Okay, so we've just lost 22 then. But there is no number here. Oh, hold on. It doesn't work that way. The minus symbol tells us what will happen when we leave this room, and the room that we enter is what actually happens, or how is the magnitude. And so here's the lock. I'm just going to draw like a lock symbol here. And there are 3 exits, north, east, and west. So north, east, and west. We'll just draw a padlock here to remind ourselves. Oh wait, no. We're in a grid of rooms. This is not... Is this a vault lock in here? I think the whole thing is a vault lock. So I'm not sure about that padlock. Let's go east again. Okay, so this one contains a 9. Oh, so they alternate between symbols and numbers. And this has north, east, and west. So we're going along the bottom of the grid, it seems. Is there anyone else making programming puzzles on this level? I don't know. I've heard of Everybody Codes, and it's very much Advent of Code inspired, and it runs in November. So I've never done it. I think I'd like to do it next year. And in the meantime, I might find some time to stream 2024 and 25. But that might be fun to do. Yeah. And then I don't know, there's Project Euler, but that's different. I I I like that it's more math focused, and I also like that it's not lead code. Well, I test if you finish tonight. I'm not sure about that. Um, when I finish tonight, I'm gonna be tired and going straight to bed. But I don't know. I'd be curious. Feel free to send your updates. um, let's keep going east. Okay, so there's this is a multiply. And let's just go north from here. And 18. Okay. So there's a multiply. Uh, maybe let's not draw it that way. Let's just do an x. There's an x. And going up, we have 18. And this goes north, west, south. So we'll just snake around. West, there is a minus. There's a 4. There's a plus. Okay. So minus 4 plus. And what I'm hoping that these number values aren't influenced by what's in the 8th register, like when the map is generated or something like that, because then if that's the case, this is unsolvable, and the numbers that we're putting in here aren't going to help us later, and we'll have to start over, which would be unfortunate. Oh, we never grabbed an orb, so it's not currently changing weight. You don't know if Bad Cop worked on it before, but she's already in the game after 1.5 hours. Oh, great. I mean, I think 1.5 hours is believable if you just went straight to like trying to hack it out. Hmm. All right, so we go north, we see a 4, and let's just go east along. East, east, east. So 4 star 11 and star 4 star 11 star. We'll at least get the size of the grid, if nothing else. Maybe the values in it are incorrect or something. And all of those had a north, right? Fair enough. But even Dave, um, I was watching his stream and he did get like sidetracked a lot. So I don't think he's on a clock and trying to do this as fast as possible. And I'm certainly not. I've been super distracted by little side quests. I know. It's it's like hard to believe, and then you watch her do it, and she actually kind of makes it look easy. Like she makes it look really approachable and possible. Okay, so we just looked at that star. Let's go north, right. And here is a vault door. So we'll cross this out. Um, so there's the vault, southwest vault. We'll still mark it like an exit, so we'll just say V because I know it's kind of like a state machine, right? And it's still a place you can go. Um, so there's the George's vault has a large 30 carved into it. There's a running hourglass, which never seems to run out of sand. So there's a 30. Oh, interesting. I think they told us what the number was in the journal. Do you remember that? Let me check. So I think they mentioned number door. The number on the door flashes black, and then the orb evaporates. Oh, 30 must be the goal then. The number on the door. So maybe we shouldn't treat it like there's a number on the floor. Okay, I'm just gonna draw it off to the side because I'm not sure that actually changes anything. Oh yes, the liquid cake puzzle. I'm wanting to do those too. Liquid cake and then El Calanque's puzzle. Man, I feel like that's what the cool kids are doing. Maybe I should get into making a puzzle. Hmm. So from here, oh wait, there's a 1. So there's a 1 here. There's a 30 on the vault. So 30 is our goal, and 1 is this room. West. So there's a minus, there's an 8, there's a star, and that is all of them. So star, 8, minus. And I'm guessing the anomalies mean there's not actually a solution to this. But we could code up a general solution. We could see how these numbers actually change the value in the 8th register if we were to reset, because that would confirm for us that these numbers are based on the value in the 8th register. Yeah, I think I want to do that real quick. Do we just do a bunch of undos? I think that's too many. I don't have like proper save states. In an ideal world, if I were wasting a lot more time, I'd create like a save command to save the state with like a little name you could add to it. Then you could do like a load command to load that save. That'd be fun. But we're not doing that. I think we're just gonna reload. Okay. So there's a jump. Oh, wait, this is normal, right? Um, so the set, or no, is that normal? Why is it accessed so early? Oh, I think this is a trap. If it doesn't start at the value 0, then like the self-test will fail because all the registers need to start at value 0. I see. So you have to change the state after it's running or like jump your instruction pointer somewhere. So we'll set R8 to a different value. Last time we did 42. Um, let's see. Let's do 13. Okay, use teleporter. Sorcerer, welcome. Good to see you. Bad Cop liked your slash notation so much she's implementing it in her Synacor. Oh, fun. Yeah, that's great. Uh, and Bobby started redoing AOC 2025 in C. You forgot how brutalist and humbling it is. Oh my god, I don't think I've written C since college. Um, the closest I've done to doing C since then is playing around with Scala native. And I think the closest I'll get to doing it again is Rust. Unless assembly counts. Is C closer to assembly than it is to, I don't know. I've been sober, yes. um, so let's just barrel through north, 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 and let that run. I need a slash command to set my typing speed because when you're just running through here, you kind of regret having it be all pretty. Okay, there's 22 carved. Okay, let's go east, east, east. There's a minus, there's a 9. So the puzzle doesn't change just because of the value of your 8th register. I mean, it might still be different if it was true or false or something. Let's go north, north, north. There's a 1 on the floor. There's a 30 carved into the vault. Okay, I think we should play with. And was everything else the same? There's a star and there's an 18. Let's play with the vault a little, with the orb a little bit and see what happens. So let's go east, 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 and south, south, south. I don't know if I did that right. I'm pre-moving. Where are we? Star symbol? South? No, we can't go south any further. We can go north or west. North or west, we're in the bottom right corner. So let's go west, west, west. I think I was crashing to the wall repeatedly with my easts. Okay, so we'll take orb. And if we're trying to get to 30, I don't know, you think we can actually just manually solve this? Plus 4 is 26, minus 11. This last thing is going to be well, times 1. Probably solving it backwards is better, right? So if we can get to 30 beforehand here, and then what I anticipate will happen is it might flash white because it's the correct weight, but then we didn't get it in the right number of steps. Um, can we get to 31 somehow? Not via multiplication. So this here seems like a dead end. So we'll probably get it from below, right? Um, so times 1. We have to get to 30 by here. Multiplying by 8, multiplying by 11 doesn't make sense. Maybe subtracting one of these two. So if we get big right off the bat, so 22 plus 4, 26. Times 4. What's that? 52, 108. Yeesh, that we need to subtract a lot. Minus 9, minus 11, minus 8, times 11. Wow, it actually seems tricky. Oh well, let's just experiment with the orb. So let's go north. North. Wait, did we take the orb? Yeah. So as we enter the room, the floor flashes green, the orb begins to glow green. Um, because we are on top of the plus sign. I'm gonna go north again. It should get heavier by 4. The orb gets heavier. And then let's go north. And it grows yellow because of the multiply. And then we go east. He shared this puzzle with a friend some years ago and was humbled to watch him solve it in a matter of minutes. Wait, early minutes. Okay, that's crazy. Depicting the number 8. Okay, so it should be significantly heavier. Plus 4, so 26 times 8. This is like 208. Yeah. Um, and we need to subtract. There are no divides in here. Okay, so we'll go east. Um, and why don't we just walk by with a bad value and see what happens? Can we walk over that and not end the thing? The number in the vault flashes black. The orb evaporates. So the orb instantly evaporates if we enter that room with a wrong number. And there's a running hourglass which never seems to run out of sand. Okay, there's probably some loop that we take here over and over again until we get there. So we're gonna Dijkstra this. I do enjoy sitting with these problems. And I do like not having the rush of Advent to where we can take it at pace and also just do other fun things on the side with it. If we could convince Eric to quit his job and offer a monthly puzzle subscription, that'd be great. But we'd need to offer him a lot, I think. By the way, did all of you do your AOC++? I haven't yet. I mean to. I know I will. Um, okay, cool. I think we've had enough of that. And let's go to our play worksheet. Let's make a new worksheet just for the Volt. And we'll solve the Volt problem. And we don't need any of the Synacor imports here. AOC++, it's the yellow text you get by your name if you donate. I don't know where it is. I haven't seen the link yet this year. Oh yeah, AOC++, right here. You can support via Stripe or PayPal. Oh, I'm showing how much I pay each year. And then you get this by your name on like leaderboards and stuff to show. So those are people that donated. Actually, that's a good number of people donating. Um, let's see our leaderboard here. Yeah, there's a decent number, but it could be higher. It could be a lot higher. Yes, the FPGA challenge. So I'm thinking about doing that too. So after this, after this, I'll be taking some sort of break. But then I want to do Liquid Cake's puzzle and Elcolonk's puzzle, and then the FPGA. Mhm. And then I'll need to figure out my streaming schedule for next year, especially after I start a contract. I won't be doing 5 a.m. every night. So the volt problem. We could just draw out a grid. and there's a start spot. Okay, so vector, you know what, we'll just do a vector comma separated strings, and we can do whatever else from there. So x, 8, minus, and 1. We have 4x, 11, and x. We have plus 4 minus 18, and we have 22 minus 9x. So this is our volt. What was it called exactly? I guess volt lock. And we'll say the goal is 30. Val goal equals 30. And the start is going to be that. So I'm going to import my AOC stuff. I'm just going to do this as usual with points. We do want a state. L colon Q. That's what I thought at first too, but I think on this page I saw it say L colon. Yeah, I think it's there in the banner. But I don't know, maybe someone can verify. Okay, so import AOC dot star and val grid is just going to be area dot, well, I guess it's the area. Area applied to our grid, so our vault lock. Okay. And then we have a state, and I need to be able to get the next states from that. So case class, or let's do an enum of our state. And then we have two cases. So we either have a number or an operator. So operator, and then we could have you know, let's just enumerate all of them all together. So we have mul. We always have a precision. So pause point, some mul, that has a precision. There's no value. I guess there's a value, our current value. So all states have a value. I guess we'll call it weight, a weight and a precision. So weight int precision point. So there's a weight int precision point. And I guess the only other state we're worried about is, yeah, actually that's it. So we already have the operator. You know what? That doesn't need to be part of our state. Like the symbol in the room that we're in doesn't need to be a part of our state. We can just compute our next value based on that. Well, no, it does. Because when we're going from here, from minus, we're going into another room. When we enter that room, it does depend on what our current status is. So we're either mul minus mul add sub, or constant, case constant, right? And I think that should do that. Extend state with wait and pause. Okay, have you resolved it? Silent L. There's a silent L? Colonc? Is it just Colonc? I haven't seen VODs of liquid cakes. And what's wrong with this? Unused explicit val, right? Val. You know what I should just do? I'm gonna make this we're turning this back into a case class here, and we're just gonna do operator, and we'll make that optional. So option of op, and we'll have an enum op. Enum op case adds submol. Okay, so that's our state. And def next. So we need next states. So given, well, we'll just put it inside a state here. So def next, and there's going to be a set of state. We don't need Copilot here because they're just messing with us. Okay, let's get this settled here. Hub.colonc.computer. How do I make a page? Hosted by Clonk on the bottom. That's fair. Okay, let me just check Twitch Clonk. No. Clonq. I mean, L colon Q is like the most obvious one, and I kind of wish that was just it. Um, Name L Colonc. There it is, right there. I think that's pretty definitive, right? Oh, it's a Vim reference. So what does L colon Q do? L Colonc. Of course, it's a Vim reference. L Colonc is a traitor to all of us. I think I think he actually went from Vim to Emacs and then uses evil mode in Emacs. Right. Colon Q does quit Vim. That much I've learned. That's very important to learn. Hmm. Yeah, is an Emacs user and a Lisper. Very fun. I think L means like the colon Q. Something. Oh, MLH. Okay. Well, in Emacs is just Control L, and you cycle. Okay, so we have already pause. So pause dot adjacent gives me my set of adjacent points. And we can filter by inbounds. So dot filter area dot inbounds. No, underscore inbounds of the area. Inbounds of the area. And then we map. And how we map actually depends on our current state. Um, Maybe actually we could turn this into a grid where we parse out one of these four. We parse out an op. Nah, we won't do it that way. Point of his handle. Yeah, it's working. We're talking about him. Very demure. Okay, so all of these P's, what we do with them, it depends on our current state. So op match. Okay, so if it is sum, then we'll do another match there. But if it's none, that means we have a constant. And we are changing our state based on what we read in this position. Right, so we'll do like a so vault lock. I'm gonna rename vault lock just to grid. Okay, we got our grid. So we get grid of P and we match. And if it's a star, are we gonna get actually, hold up. We've got to comma split those. So dot map for each of those. Underscore dot split. Oh my god, it is lagging out a little bit. So underscore dot split based on the comma character. Okay, that should do us there. So this is an array of characters. So if it is a star, then we change our state. We change the op in our state. So we would do this dot copy, and pos equals p, and op equals sum mul. Okay, that works for us here. You know what? I do want to wrap this in. We'll say const or no op. Let's say no op. I just don't want to deal with I know. I don't want to deal with none and some there. So this is op.no-op. So if it's no op, we're going to gain an op, and our op here in this case is going to be op.mul, right? So we're matching based on the grid. We'll have 3 of these lines. If we see a plus symbol, then it's op.add. And if we see a minus symbol, it's op.sub. I just realized it's kind of funny here that I decided to make something for myself to parse. I could just construct this by hand, but I'm like, I think I've been trained by Eric to where like I have to have something to parse. So I have to give myself something to parse. So here we go. Otherwise, if we are op.mul, then in this case, we take the value of the grid. So val n equals grid p dot to int. Is it going to be a character? These are actually strings. Let me fix that. Advent conditioning for sure. So grid p dot to int is our n value. And we do copy, and we set pos still equals p. Our weight equals, in this case, it is we are multiplying by n, right? So weight times n. And then our op goes back to constant, I suppose. So op means just whatever the floor was in the last room we were coming from. Okay. And I'm happy letting Copilot complete the rest of this. There we go. And there is no such thing as op.const. So Copilot just happily went with it. I guess I'm renaming to const then. Okay, so we've got our state transition function. Grid P. Oh, there's no P? No, there's a P right here. Hold up. Op is our current state, right? Let's make sure we're getting this right. So let's say we're moving from here, this 11. Our current state then is a const. And in that case, in these other rooms, we should be seeing symbols. Right, great. And if our current state was like this x here, then we are a mul, and we should be seeing numbers. And we will multiply by that number. But now why is this P not working? Found point required int grid. I should be able to apply that. Dot apply. You know what? We're gonna map these to vector. I think it just doesn't like array being in there. Okay. And def search. Okay, so we are looking for. We're looking for the full path, aren't we? Yeah. So we're gonna import collection.mutable. What is it? We want a queue. We want a priority queue. And I think we'll also want a map. And I don't know what search is returning yet. I suppose it's returning a state. It's actually going to return a list of states. So we'll need to make a graph as we're going along here of like parents of each state. So that we can construct that list. Desu, hello, welcome. So we have our start. So we'll say just our current. Current equals state, and it's gonna be this one here. What's that gonna be? Point each. I don't even know. I never actually know whether my y's go down or up. So I always just grid. Let's see grid at the point 0, 3. Not found point. Oh, right. Let's put our import here up top. And we have little compilers, I guess. Oh, this is in a different file altogether. Why it always goes up, always go down. You know, I think that's happening sometimes, and then I realize I'm solving the whole problem upside down. Um, the way I draw it or something. And it never actually really matters which way is up or down, as long as you're consistent, right? So I think when I draw it, this is 0, 0. And it is convenient to work that way. Okay, so in our vault worksheet, where are we? Oh, right. Just comment that out for now. String 22. Okay, that is a start. So var current pause equals that point, or no, wait starts. I suppose the wait starts at 0. The floor of this room is a large number. The orb flashes red. It still has a 30 carved into it. I want to try something. I want to see if that number actually changes or anything, because we don't actually know the starting weight of the. We can assume it's 22, I suppose. But maybe 30 is the current weight, right? And we never just see what the value is there because it resets when we enter it or something like that. I don't know. I have to try this, even though it might be dumb. Is this past the teleporter? Yes, we are past the teleporter. So we're gonna take the orb, and we are in this maze here, right? And as you go through, it starts computing an expression. Let's go. Let's go east, and let's go east again. Now it should be lighter, right? So let's just drop the orb, then go north, 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 and then east. Okay, it still has a 30 in front of it. Okay, I know it's silly, but I just had to check. So let's assume then that the weight starts at 22. Position is 0, 3. Mm-hmm. And what's the other thing? I guess the op starts at constant. Op equals op dot constant. Right. And when we're constant, we're gonna walk into a room and change our op. Give ourselves an actual op. And how do we prioritize this priority queue actually? The one with the fewest number of steps. So we need a cost map. I assume that the hourglass implies that, we want in the least possible time. So val cost equals map, that's going to be a map from a state to just an int. And we'll say current goes to 0. Yeah, that makes sense. And then priority queue, val pq equals collection. Oh, wait, no, we just need priority queue. Priority queue of current. And then we're going to use an ordering using ordering dot by cost, which means the highest one is what we're going to do first. We need to reverse that. Ordering by cost dot reverse. Okay. Catch me if I'm flipping something there, but I think that's correct. And we also want a parent. So for val map or no, val parent. It's going to be a map from state to state. And yeah, this cost is not going to have a parent, so it's going to just be a map.empty to start. Okay, now while I guess we have an end state in mind, so val end is going to be state weight equals 30. Oh, and before I forget, let me just add a to do up here. So to do avoid the top right, because as soon as we enter there, it disappears. The orb disappears. So we need to make sure not to walk into there unless it's going to be, yeah. We'll think about the specific case there. Okay, so weight is 30. Position is going to be, what is this? 1, 2, 0, 1, 2, 3, and 0, 3, 0. And the op, I guess the op doesn't matter. But I mean, once we enter that room, the op becomes const, right? Yeah, we enter a room with an n and become const. Okay, so that's the end state. So while current is not equal to end, then we do stuff. On AOC related blog post. Okay, cool. We'll pull that up in a bit. Okay. And no, this is a while do. Okay, so while do. So we're gonna take current state, current dot next, and we're gonna filter on those. Let's do this in a for loop. So for I had no state in current dot next. And what are some conditions? So the cost is always going to be like the min cost to reach that state, right? So we make sure we dedupe our state. So say if not cost dot contains s, and what else? I think maybe we can put the filter in here for the top right. So if well, let's see what is exactly if the position. So if current or no, if s dot pos equals 30 or equals n dot pos. Well, we want to make sure it's not both the case that those match and we are not the end. So we want to make sure it's not both the case that those match and s equals end, right? So we don't want to be at the end position unless we're fully at the end state. Yeah, I think that is fine. There's got to be a way to simplify that. We could De Morgan it. I think it reads well that way. Whatever, we'll add parents to balance it. Okay. Or yeah. And is there anything else we want to filter out? I think that's good. So in that case, then we'll enqueue that. pq.enqueue just that s. Before we do that, though, we have to have a cost for it. So cost of s equals cost of current, I suppose, current plus 1, yeah? And then parent of s equals current. Okay. And then after doing that, for all those next states, we get our new current state. So current equals pq.dq. Cool. I'm definitely AOC trained. I don't know, before AOC, if someone had like pulled me up in an interview and been like, okay, let's do a Dijkstra search, I'd have been like, you have to look at Wikipedia. Um, so after we do all that, we do still need to make the whole list. So we start from the def path. We'll just make this recursive. This gives us a list of state. And we start with, I don't know, some state S. And then we look at S, we look at S's parents. So parent dot get S can match exhaustive here. So if there's no parent, then that's it. S is the last of it. And do you want that cons onto everything else? Yes, maybe. Otherwise, if there is some parent, then we want the parent of that. Oh, you know what? I think we want to build this. Let's build a queue instead because we're building it backwards. Collection dot mutable dot queue immutable dot queue. Okay, so we look at the path of parents. And I guess on top of that, we enqueue S. And in this case, we just return a queue. So let's import this properly. Import that. Okay. And actually, I think we are building this backwards. No, this means that our current state is the most parent. And when we enqueue, we are enqueuing to the right. No, I think we did want to do. No, we are enqueuing to that right. So the path from the parent down, and in queue we add to the right. whatever our current state is of that. Okay, that should work. Okay, so path from the end going to, is that what we had in mind? Yeah, path from the end dot to list. That should get us our answer. Um, so we should just try that. So search, um, yeah, val ans equals search. And we have some issue with this. There's a match error somewhere. Oh, there's an X. Ah, we had typed a star. You need an X. And the worksheet is evaluating. And it's already taking a few seconds, so that makes me worry a little. Do we see any issues with this right off the bat? I think I might need to run this in, yeah. We might need to run this in a REPL and do some print lining as we go. Let's just print the current state at every loop and see what's going on there. So print line, the number of steps and the current state. So cost at the current state, and then just the current state. Current. That should do it, right? And we might need to have like some sort of smart heuristic, but maybe seeing how this evolves will give us some heuristic and we can like A star into this. But geez, it goes down and up and it can multiply. Like, that's not really good for a heuristic, is it? Okay, so let's run this in REPL vault.scala. Let's indent all of this. And I know, let's give this package Synacor at main def vault. We don't need those. You said this is A star? No, this isn't A star. This is just extra. I was thinking for a second, like maybe I could do an A star, but I can't actually think of a heuristic that works with this right off the bat. Val ans equal, yeah, we'll just print line ans. Okay. Let's give this a run. Synacor.volt. Okay. Oh, we are getting overflows pretty quickly, actually. And you know what? It might be the case that we need to be doing this in U16. Right? And maybe we are supposed to rely on the overflows. How are we getting overflows so easily? I guess when you have all those multiplies in there, they add up pretty quickly. Yeah, exactly. That doesn't overestimate the cost of the goal. Yeah, because it's pretty wild and unpredictable. how the values can change. There are subtractions. Are you sure there are overflows? Yes, I suppose it could be getting negative. So let's do this. When we subtract, so the ball is supposed to disappear, right? Um, according to the journal, it disappears sometimes when you walk into a room. I think that's when it goes negative. Uh, so let's filter weight is non-negative. If s dot weight is greater than 0, let's say greater than 0. We could test this for sure, but let's just say that for now. To do verify. And we could test if, like, we could try to overflow it. How many times would you have to multiply the biggest number in there? We could try to overflow it and see if that also sets to 0. Oh, we'll put that right here. Well, if we need orb underflow. Yeah, exactly. But what's getting me is we don't have negative numbers really in the Synacor VM. So what if we are just supposed to let it go? Yeah, I don't exactly know what the condition is for it to disappear. Right? Like, how does the Synacor VM detect negative or detect an overflow? Mhm. Okay, well, let's at least do that. We'll do that. We'll give that a shot. Should at least decrease our number of forks. Um, but I think we probably need to do these on literals. Mm. And I suppose we could do. Mm, this is a lot of states. I'm not completely sure there isn't duplication in there. No, there can't be duplication. It just grows a lot and very quickly. But we're certainly already past our max value, right? Let's see, what is our max value? Let's pull up the worksheet. Synacor dot numbers dot lit dot max value, or u15 dot max value. Oh, it's trying to search. Let's cancel that. Oh, it's indexing. That's not what we want. Okay, we haven't killed it. Okay, whatever, REPL here. Um, it is 0x 7FFF. What's going on up here? 32,000, yeah. That's our max value. Hmm. I think we need to do overflow detection. So what we could do, feel free to ignore you because you're distracted when you implement it, but can you explain the search? Yeah, so this is a Dijkstra, and I'll be happy to explain it because that means more opportunity for people to debug. So we start at the starting state, right? And then I have here a map to store my cost and a priority queue that's sorted based on the cost. So I'm using this trick I do where I just um, ordering takes a function, right? So I can construct an ordering to pass to priority queue. And normally this is an implicit, so like it just uses the natural ordering of the numbers. But I'm given an explicit one here, and I'm ordering by a cost. So this takes a function. A map works as a function, right? So I'm just using this map as the function. And as the map updates, so does anything you put into the priority queue uses that updated map to decide where to put it in there. But anyway, I have a priority queue based on the cost, and then I also track the parents of each state. Um, and then for each, so I have my current state. For each state, I look at all the adjacent states, and then I filter out a few cases, right? So I'm going to filter the overflow stuff, but I make sure I dedupe them so we don't already have a cost for it because the cost is already going to be the minimum cost. And since we're searching based on that priority queue, we're always going to take off. Well, I'm getting ahead of myself. I have an edge case here for the top right corner because it's weird. You can't walk there before you're done, or else the ball disappears. So for each of those new states that are adjacent, I update the current cost. I give it a cost of the current cost plus one. I set the parent and queue. And then I take my next current off of the priority queue, which is sorted by cost, right? So I'm always taking the lowest cost states and searching from there. So just a classic Dijkstra. Um, and then I use that to rebuild this, to rebuild the path to get there. I used a parent map. But I think I need to use U15 because the game is almost certainly not doing anything bigger. So weight is actually a U15. Let's import synacor.numbers.star. And weight here is going to be a lit. And I think after we do one of these, we need to do an overflow check. So I suppose I could implement an alternate to these. And I could check if any bits are set that are outside. Same with here. And I suppose same with, actually I wonder how minus is happening. It's probably just adding to a number that has a top bit set. In which case, I think minus depends on the overflow to work properly. So I don't know. But I think at the very least, a positive first step is changing this to a lit. And we even mention int anywhere else here. So weight is a lit. Here we have to do 22.2 2 lit. End state is 30.2 lit. Weight is greater than 0.2 lit. Go. Actually, at this point, you can't have a negative lit, so that doesn't actually even matter. Is the cost related to the weight, or is it just the number of times the room was visited? Yeah, it's a number of steps you've taken, so the cost is the number of steps. Because we want to minimize the time that takes to get to the top right. But at this rate, we're struggling to find any solution at all. Whoops. One too many control C's there. But yeah, still have to figure out what to do with the overflow. And we still kind of have to figure out the reverse engineer the Ackermann function, don't we? Okay. We'll let that run. Oh, we have some issues somewhere here. Wait, where are the issues? Value minus is not a member. Wait times n bound int. Oh, n needs to be 2int dot 2lit. And we still have issues here somewhere. We found an int. In our state transition function here. Oh, yep, you have to do 2lit everywhere here. Actually, you know what? Let's just do it this way. We'll condense all these together, and they all start with this line. And then the new weight depends on this. So we'll do weight equals about new weight. It's going to be op match. Op match. Uh-oh. That doesn't sound good. I think we've killed our worksheet again. Op match. Yeah, that's why it's not doing it. It's a case op.mul. And we can just do this part here. Wait times n. Right? And then do something similar for the other two. And then this line here, we just have new weight. Weight equals new weight. Now let's let Copilot autocomplete this. Okay. Let's give that a run. Weight minus n minus non-mem. Oh. Right. Well, how do we subtract? I suppose we could do plus negative n. Will that work? I don't think that's quite right. Let's do console here. And we'll do some testing. I think we'll need like a +1 in there somewhere. Import synacor.numbers.star. Okay, so let's do 10 dot 2lit plus we just want to do -1. So 0 negated is -1, right? So if we're going to subtract 1, we would do 1 dot 2lit plus 1.2 lit, and then we negate that whole thing. Or no, hold on. We would actually use a negation first. Yeah. So if you want to subtract 5, you would do it that way. Okay. So we bitwise negate, and then we add 1. Bitwise negate, and then plus 1. Up to lit. Okay. And I don't know what to do about an overflow check. I do think we want to check. Maybe we want to check that the first bit, the highest bit, is not 1. Let's add that to do here. Check highest bit is not 1. Yeah, I learned that at some point. Probably in like college architecture class. It comes in handy here. Okay, I mean, so we have fewer states, which is nice. No element removed from heap. And then we hit a dead end. Wait, these are all at 0.00. 0.01? We're not moving. That is weird. Okay. Did we forget to update the position? Okay, let's go back to, well, we're gonna copy over our state transition function to the worksheet. One feature I'd really love to have is just the ability to run a worksheet in SPT. And I think I could have a workaround for that if I use like Scala CLI. Mm. So I don't have to just copy back and forth. So next, let's test our next state. So let's get a val s equals that. And just do s.next and see what each of those look like next for each print line. Are we actually moving around? Is our worksheet dead though? Yeah, our worksheet is dead. We'll restart that. But that looks suspicious, right? That is real syntax. It is dead code. It shouldn't get hit because that's handled by an earlier case, right? Op.const is already handled up here. So I know that's dead code. This triple question mark, it's not actually syntax. It's actually a function, or it's a value. It just throws an exception. So the definition of this value is throw new exception. And it's of type nothing, which is the lowest type, which means you can use it anywhere and it will type check. Yeesh. Wait, AOC.set. I think that's confused. Okay, that worksheet is very confused, but let's go to this file. This one's important. This is what we're actually running. And what was the issue we ran into? Yeah, we're not seeing any actual moving. So when we get next, and we should always be getting new points. So adjacent.filter inbounds area map. Um, okay, if it's a constant, pos equals this new point, right? This p is a new point. And in this case, the p is a new point. Hmm. That's weird. That's really surprising. Oh wait, it's constantly constant. Why are we never seeing other states? And then we see a bunch of moles, I guess. That's always at the same point. I've got to explore that in the worksheet. Okay, is this compiling properly now? S.next for each print line. Otherwise, I'll have to do this in the console. There are problems in this file. It's not compiling. Not found type lit. Okay, fair. Import Synacor.numbers.lit. Oh. And I think, no, we'll just use dot star, all the numbers. Dot to lit. We gotta do that everywhere else. Dot to lit. I suppose we can just comment out this whole search function. We're not using it. Okay. Okay. So we start out at 0, 3. Here we get 0, 2, and 1, 3, right? So we're gonna do s.next dot flat map next, and for each one. Copat knows exactly what I want to do. Okay. Now this gets us, it should get us fewer points than that, I think. Well, we're not doing the filtering. State 0, so we subtracted the thing back. 0.03, 2301, 1203. That looks fine. Let's flat map and let's filter. Not filter inbounds of the area. Dot pause dot inbounds area. 1, 2, 3, 4, 5, 6. Is that too many states? Well, it's not too many. Right, we can get to the same position in a couple different ways. So 0, 3. This is back at the origin, right? 1, 2. After 2 steps, there should be 2 ways to get back to the origin. So one's by adding 22 to itself, the other's by subtracting 22 from itself. You know what? That'd be a decent test. Why don't we see what happens when we get to that 0? And then we'll try what happens when we get to a negative number. So let's run. Oh, I think we want a new save state for our the problem is to get to the teleporter, we have to mess with the state on the way. So we can't make a save state the way we normally do. I think we can figure something out to have a save state for that. All right. So we'll set R8 to anything. Set R8 to 100. And we'll use a teleporter. And then we'll go north, 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 north. I think that will get us there. Oh, no, not quite yet. There we go. So let's get our history. Oh, there was an author or two in there. So there was a look, and then we just need these. Let's go to our main class, and we're gonna make a new shortcut. Val 2 volt equals list. So let's do all these. We'll filter out the typos. Add a comma on the end there. Okay. And we can move this look down to the bottom. And now at this point, we need to set the register first. Emu equals emu dot set register. R8 to I don't know 100.2 lit. That should do us, yeah. And then we run the 2 volt commands. So emu equals feed multiple 2 volt map, yes, all that. And then same progress until blocked. Remove the output queue. Wait, don't I have a clear output queue? I don't think I have that command. I should have it. And at this point, we feed a look and we go on from there. Okay, so now we have a save state for vault. Okay. So there's the orb. Let's pull up our map. And what I want to do is try out the 0. So take orb. We're at 22, right? I think we start at 22. Maybe it's the case that we actually start at 0. So from here we go east. And then we go back west. And that should put it at 0. The orb evaporates from your hands. Okay, that confirms it. Well, that confirms that we either hit negative 22 or 0. In either case, 0 or smaller will ruin it for us. Yeah. What's like the fastest multiplication loop we can get? We can keep getting this times 18 minus 11 times 18 minus 11, I suppose. Or is it faster to go times 4 times 8? Probably this one here. Yeah, because that's times 32 each time. That will very quickly get us up there. And maybe we shouldn't be doing an extra search here. Maybe we should be doing some math, something smart. Or maybe we should be searching from the end, from the opposite end. and searching for 22. It's actually just the same problem. It might actually just be the same problem. If you go east, north, east, east, does it vanish? Yeah, good test. So east, north, east, east. Because that should get it to 18 minus 18. Well, that should get to exactly 0, right? So take orb, east. So it's not 18, north. No, now it's at 18. East, east. Wait, what? It did not vanish. Because if we start at 22, minus 4, down to 18, minus 18, we should be at 0. Did I do that right? So there's the orb. We take the orb. We had a minus. We went north. And there was a 4. We went east, minus. Yeah, I suppose maybe just getting to negative. Okay, let's go west. West. Okay, we're still negative. This is -4. Maybe it's specifically 0 that will do that. Because then, like, we have unsigned integers, right? So we basically just if we make the 15th bit a negative symbol, then we're down to like 14 bits of integers. Wait, it's shattered? The orb shatters. Oh, that's weird. It's shattered rather than evaporating. Interesting. Okay. So if we go back, here, what actually happened? Wait, I went back too far. So where do we see the orb again? Okay, we took the orb. No, as you enter the room, the orb evaporates out of your hands and it materializes on the pedestal. Okay. Interesting. So it shattered when that 15th bit was set after doing subtract specifically. Okay, let's just try 22 minus 9 minus 18. That should shatter too, right? So let's go, man, I wish I had implemented save and load. Instead I only have undo. So let's go south. South? Wait, where are we? We're already south enough. Let's go west. Here's the vault. We can take the orb. Take orb. And let's go west. So this should drop us to 13. Or east. Should drop us to 13. If we go to the 9, right? And now let's go north. And if we go to east, it should shatter. The orb shatters. Right, because in that case, we went to what, -5? But why did -4, -18, which should have hit 0, not do anything? What other paths do we have in here? -4, -11, -8. So that would be 15 minus 8. I would guess in -1. I think maybe it'd be helpful to see the code that runs when we do this. So maybe I should do a function extraction. Ah. And the useful thing to do might be to find where our current weight is written. Right? If we diff the memory, I'll need to make a memory diffing tool. And it actually might be in the registers. So we could try like getting to the same room with two different paths and then diff the state of those two. And now right now we have a way to quickly get to a room. So we could actually do that pretty quickly. Yeah, we could load them up in a worksheet, look at index where memory is different, print that index, examine that index. Okay, so I think before we do that, we should test that our save state works. Okay, perfect. So let's take this, and I just want to do that path to -18 again. That is a perfect path because that goes exactly to 0. And let's go further from there. I know times 9 should still be 0. Take orb. And let's go east, north, east, and east. The orb gets lighter. Maybe this is where like the anomalies are actually playing in. And I'm not seeing the expected behavior because I didn't set the register 8 to the correct value. Um, let's go south and then back north. It didn't say anything about the weight changing, even though normally when we enter a room. Oh wait, it's when you leave the room that happens, right? -4. No, it's when you enter. Okay, we'll just keep going south again. So south. So now we're over the multiply. And then when we go north, it should multiply by 18. And it doesn't tell us that it got lighter or heavier, right? So that tells me that we are currently 0 because repeatedly multiplying by 18 is doing nothing, right? North, south. Now we are in a dead end though, because anywhere we go, actually, let's go north. So we're at the X now, and we can safely go all the way over here while staying 0. So we're gonna go west. Times 11 keeps us at 0. And then times 4 will keep us at 0. And then we get plus 22. So let's go south. And then south. Huh. Interesting. So we're at 0, and we did plus, and we walked into this room, and it disappeared. It evaporated out of our hands. Um, and I'm trying to wonder here, is it just because we re-entered the room? I don't think this math had any chance to execute. We entered the room and we had an orb in our hands that was 0 or less, and it disappeared. Or is an orb in our hands that was 0 and it disappeared. Did the journal actually talk about shattering? Because okay, so shatter. Nope, it does not talk about shattering. Evaporate. Okay, it simply evaporates if we try to leave with it, but another reappears. The number, so the door flashed black, and then the orb evaporates. So if we reach the vault door, um, it eventually evaporates and a new one appears as usual. If you walk through a certain room repeatedly, it gets lighter and lighter and eventually evaporates. So the shattering we're seeing must be an anomaly, and what we're supposed to be seeing is evaporation. Uh, and here's one. Every once in a great while, one of the crew members has the same story. The door flashes white. The hourglass is already run out. It flashes black, and the orb evaporates. Right. So once in a great while, someone gets there, but they were too slow. Hmm. Okay, I mean, they spent 144 days. I think I could just run a brute force for 144 days, right? Um, but right, we have to avoid going negative, whatever that means. And we still actually have to handle the Ackermann function. Okay, I think this might be a good place to like set that aside for a sec. And I don't think I'm gonna finish tonight. So I'll need to sleep on this a little. But we could set that aside and we could look at the Ackermann function. And we could at least try to get the correct value of the 8th register, and then walk around these rooms again and see if the right thing is happening. Um Actually, let's make a list of all the things we want to do. So let's go to README. So we have, oh, we do have hooks for RA access. That's nice. Read the journal, scout ahead in the new area. Yeah, we've done that. So we still need to figure out that correct value, but diff vault door memory. This one we can do very quickly, actually. So maybe we'll do that first. We still want to do the Ackermann. What else did I say? Mm, That's actually pretty reasonable. Just the memory, do the Ackermann. Okay, let's open up a worksheet. So let's go to our play worksheet. And there were all these functions we were extracting. But what we want to do, okay, so at this point we've used the teleporter. We need a play, let's say play vault. don't need all of this. So start PM. I'm going to copy from our main file because we have a good shortcut there now. Okay, so we have a start VM. We start messing around with our emulator. Here, our emulator is defined here. So we use a shortcut, we use a 2-volt. And at this point, we don't need to look. None of this stuff we need. Okay, so at this point, progress into block. Let's why don't we use the output emu.useOutput just so we could see. Emu equals emu.feed look new line. Emu.useOutput print line. Just to verify this is working. Input too long. Oh, did we not? We need to progress until blocked first. Oh, we did want to keep this bit here. We want to keep that. Okay. On an empty queue. No, we progress until blocked after this. Okay, now we should see our, wait, that's use output. What does use output actually do? String output q.dq. We just take our output string and print it. And then it does have a return value. Oh, I see. The output is, the comment is too long. The output would show after all that. Okay. Well, whatever. We know it works. So at this state here, we know that we are at the vault door. So let's pull up our map. And we're gonna go west. Feed north. Dot progress until block. No, not north. West. West new line. Progress until blocked. And I think I need to make a copy. So val emu2 equals emu. So west west northeast. And just west north. West west north east. And then the other one will go emu dot feed. So west that progress until blocked. So this just goes west and then north. And we want the memory of that state. So dot state dot um, if it's progressive blocked, it's going to be an input. So we're going to get that state. It's going to be an input, so we can make the other three triple question marks. And we want the memory, so F applied to a character like space. And hopefully that doesn't mess with anything. This is still kind of a hack. I mean to change my emulator so it has the actual state rather than ticks. And then dot memory. Okay, val mem2 equals emu2 dot all of that. And val mem1 equals this same kind of thing. So emu dot state match, all of that. Okay. Triple question mark. All right, and let's see. Mem1 equal to mem2. False. Great. So let's do mem1 dot zip mem2 dot index where one is not equal to the other. Oh, mem1 dot underlying zip mem2 dot underlying vectors. 2732. So we can start exploring at 2732. Or what we could do is we want a full proper diff actually, because that could just be anything. So 2732. Let's do that again. Index where should have an alternative where you start from somewhere from, yeah, you start from an index. So let's see if there's like a sequential thing or I don't know. So 2732 plus 1. And let's see where the next index is that they are different. Like there could be all kinds of things happening, right? There could be like stats of a run being saved somewhere. So there's like some metadata and it could just be like number of steps altogether. Maybe they're like objects being created on heap or something. And I don't know where the boundary is and where heap starts and where the ROM ends. So differences in memory could mean anything. And 2733. So there's a sequential group starting around there. Okay, well, let's look at 2732, 2-hex string, and maybe we consider 2-hex string. Maybe we consider doing a sweep for that in our VM state so that we get alerts as we run through that. And see where like the address of that command was. So AAC. And now I think while I'm at it, I should compare the registers. So I'll name these state 1 and state 2, S1 and S2. Well, mem1 equals that. Okay, and let's do a similar comparison with the registers. Mem1 dot or S1 dot registers equals S2 dot registers. Is that true? Okay, even the registers are different. Interesting. Like, I wonder if register 7 is being used or something. So we can just straight up print both of those. So S1 dot registers dot underlying that make string with commas, and do the same thing for S2. Where do they differ? Oh, right, because they're arrays. Okay, they have the same values. Yeah, okay, never mind. The registers are the same. I forgot we were doing equality on arrays there for a sec. um, I, I don't actually like that makes these unequal. That's a little flaw. Maybe we'll leave that as a to do. Um, to do fix register bank equality, because I want those to be equal. Surely they have the same program counter, right? So S1 dot PC equals S2 dot PC. Right, they're at the same place waiting for input, of course. S1 dot anything else? Stack should be the same. Oh. Okay. Let's look at this address. 2732, no, AAC. It's going to be up state. Let's look at when that gets hit. Where is our tab? Check our rates. We'll just tag it onto here. If instruction string contains AAC, so 0x0 AAC, let me just double check that. Where did I done that? This one, 2732.2 hex string. Okay. Then, I don't know. Mem 0x0 AAC access. Alrighty. What's going on here? Instruction string. Bad autocomplete. All right. It seems like that's accessed quite often. So that isn't the memory that we're looking for. It's a block of memory that well, it's quite often at this instruction here. Hmm. Okay, let's go. Let's go east. See what happens. Yeah, that gets accessed quite often, so that has nothing to do with this. Um, okay, it was worth a shot. It at least tells us that we have to think a lot more about where. Oh, here there's a write instead of a read. Write mem to that register. It at least tells us that we have to think a lot more about the memory layout of this thing. Right? If Synacor is managing its own heap, then that just makes this a lot more complicated. And the address of whatever thing gets saved could just depend on, right? Like if you're setting aside memory, a block of memory, and then you're clearing that block of memory, it's not necessarily the case that that gets reclaimed and that memory gets reused, right? So it depends completely on how the runtime is working. That could be saved anywhere in memory. Uh, so that won't work. Um, but what I think will be more useful is just looking at the code that runs between two of these. So we take the orb. Um, I think we want to turn that off. Yeah, I think we do need to turn that off for this sec. We should do that with a flag of some sort. Okay, we take the orb, we move north, we see what objects are run. uh, Uplog toggle. I actually want to see what happens when we take the orb. And you know what? I think I need to stop logging operations that happen during input. No, no. I think those are important. Because that just goes into the next output and the input. So yeah, we just have to take everything. So uplog toggle, take orb, and that's potentially nope, I don't know. We'd have to do the same thing we did earlier where we logged all that. We found all the calls. Maybe I should filter that only for calls. That'd be a lot more helpful. And then we extract those functions. Interesting. There's an idea. So let's go to the emulator. And we have a print line in here somewhere. And we should actually have this in both parts. Oh yeah, we do have it in both parts. No, we don't. So that doesn't happen during the input. Val s equals that state.showInst. And then we will print that, but first we'll check, I know if s.contains call or s contains jump true, jump false. I guess we could get a set of anything that jumps of any type. So if set call jump, yeah, all those exist. S dot starts with. I don't think it's S dot starts with, but S dot contains. Then we print line. Okay, that should do us. And we do the same thing down here. And I'm just going to copy paste a couple times. Alrighty. One more time. So we take orb, we see what functions are called. Oh, wait. Drop orb. Toggle op log. What? Op log toggle. There we go. Now we take orb. Those are all calls and jumps. Wow, there are a lot of them. Well, no. That's just everything. So nothing changed. If there exists in this set an element such that, I know, there's an op such that s.contains, no. It needs to be op.contains. So underscore.contains. No, s does need to contain it, right? S is the full instruction. S.contains the op. Then we do a print line. Oh, this line is not deleted. That's what's wrong. Okay. One more time. Okay. Op log toggle. And take orb. Cool. That's potentially a lot more helpful. I still don't know like where the IO functions are, but I'm sure the IO functions get called a lot. It's actually a lot of calls. So let's go north, or let's go west, and then let's go back east, or east and then back west. Go east. I think we need to look at the difference between these two. And I think we'll probably have an easier time doing that in the worksheet. That's just too much. Live is too much. Back west. The thing is, last time we were finding functions of interest by just looking at what's called the most often. In this case, what we could do is walk from one room to the other, carrying the orb, not carrying the orb, diff what happens. And by what happens, I mean diff the uplog. So let's try that. We'll go to the play vault worksheet. So here we went like west and north. We did all that. I don't think we care about that as much anymore. So we'll comment it out. Okay, so we're at the door. Have we taken the orb? Oh, wait. In these two, we never even took the orb when we were looking at the diff states. Okay, so we're gonna do emu dot feed take orb dot progress into blocked dot feed west dot progress until blocked. And then we're gonna take emu2 and do just the west. But first we need to enable the oplog, that toggle oplog in both of these. So emu2, emu and emu2, that toggle oplog. And then after that, we want the oplog, the oplog. So val log1 equals that, val log2 equals that. Oh, you know what? We didn't even need to make an emu2. We can just reuse emu for this. I forget that emu, well, while we're saying it's a variable, is actually mutable. Okay, yeah, we're taking the exact same state, and on both of them we toggle the oplog. Oh, wait, we forgot to take orbit. Oh, yeah, we want to take the orb here, and we don't want to take the orb here. And so we compare those. Log1 dot size, log2 dot size. How different are they? Wow, so many more instructions. Okay, so log1 dot what if we just diff out everything from log2 in log1? So like log1 dot diff log2. And then we look at that. Let's see the size of it. Right, like, do we have a lot of similar lines? Yeah, and in here somewhere is a difference. Or, like we look for unique calls. Let's say log1 calls, log1 dot filter. So on the instruction, that one equals dot opcode dot op equals opcode dot call. Okay, so all the calls from 1 and all the calls from 2, right? Um, and then what can we do with those? Well, first let's just see the sizes. Dot size, c2 dot size, and let's do counts. So c1 dot what is it? Group map reduce, a little idiom. So we're going to group by the actual instruction. And then get the counts. And let's do a for each print line. And we do the same thing for C2. Okay. 300 calls, 179 calls. And here, oh, wait, we want to sort dot to list dot sorted. Sort by the count. Okay. And I think we want to sort them in reverse. Reverse. Val counts. Okay, counts for each print line. Whoops, what happened here? Okay, we've got the counts. So in this one, R6144, there's a lot of this register 6 calling, which I don't like. because that's transparent. We can't see what was placed into register 6. I mean, I suppose I could. I could unnest that and look at the value inside of it. Or I could like dereference it. Oh, and I probably do in the string version. 84D. You know what? This will be easier to see in a Scratch file. So we'll copy the worksheet output and open up Scratch 3. Okay. So they both make calls there. What's unique though? I suppose I could just ask that in the worksheet. 683, this 5B2, OX5B2. It's called a lot here, but not called at all in the other one. 607, 684. Yeah, that's it. Okay, so let's extract that function. Where did we do this in our play worksheet? I suppose we need this, don't we? Yeah. UX5B2. Oh, you know what? We have looked at that before. We have actually looked at that. So we don't need to extract it. It's already extracted. Oh, it's an XOR. Okay. Interesting. Oh, wait. They both have it. They both have. Okay. You know what? Let's actually try and diff those keys. Okay. So counts one dot keys key set dot diff counts two dot key set. Counts one is a map, right? No, it's a list. Um, there we go. Oh, we actually want to move that here. We just want to keep the counts separate. Key set, yes. Okay, 1721. 1721 is a unique one. All right. 1721. Okay. Let's copy that worksheet output. Back to Scratch 3. And where is that 1721? Okay. So this is what happens when, let's see, let's figure this out here. In one case, we go west. No, that's not it. Just pull up the actual table worksheet. Okay, so in one case, we take the orb and then go west. In log one, we take the orb and then go west. And in the other case, we go west. So when we're holding the orb, this function here gets called. And we push R2, push R3, set R3 equal to R1. So R1's an argument here. Set R1 equal to that constant. Set R2 equal to that constant. Interesting. I wonder what those numbers are in English. Huh. Wait. 273815964. Those don't ring any bells for me. And then we call 607, which I don't know what 607 does, but there's a chance we've looked at it before. I know it's gonna be in Scratch. 0607. There are lots of instances of it. Let me check. Oh, okay. This is interesting. So we're checking against max value. If R1 is max value, and if R1 is max value, which is say like -1, basically. You hear 6027? You heard wrong. It's 0607. I'm gonna is that a spoiler? But this is interesting here. So there's an equality check to see if we are at the max value. And if we are, we jump to an address. Oh, fuck, we're not printing the addresses. An address, which I would like to see. We had a version of this that printed the address, didn't we? Yeah, all I hear is 67. All right. Um, play.worksheet.sc. Right, this is the wrong version. We want play.scala in here. I thought I'd updated the worksheet too. I guess not. Yeah, I'm just gonna run this in another line with our new favorite function, 0607. 0607. And here we get out of here. We're gonna run Synacor.play. Okay, and here we have addresses. So there's a jump of false and a jump of true. Or no. We check. Where's the equality check? Set R1 to max value. No, this is different. Oh, the first thing this function does, this is 1721. And one of the first things it does is calls that function. Okay, but what you want is 1721. Let's take a look at that. 1721. OX 1721. I should just have a function that does everything there, including the printing. Instead of like copy pasting the same thing over and over, as if we're not a programmer. Okay, was that right? Synacor.play, cool. So the 1721 function. We set R1 and R2 to these weird values. I don't know what they're. Yeah, are they like prime numbers or something? I might Wolfram Alpha one of those. We'll take a quick look. Two 7831. It's 3 times a big prime number. And it's binary form. I don't know. That's a dead end, I'm pretty sure. Anyway, we set two weird numbers into register 1 and register 2. We call this function, which does I don't know what. Presumably it saves its value in R1. And then it compares it and jump if true to 1744, which is down here. That zeroes it out. Okay, so if R1 is at the max value, we zero it out. So is this supposed to be like an increment function or something? Otherwise, we add R2. We save to R2. We add 6A F5, right? We add this one to R1. So if R1 is not at the max value, we add this value, and then we add 1, and then we add 1, and then we add 1. That's weird. That makes me think we're kind of doing subtraction. We are doing subtraction. Right. So I need to look at these two numbers in bits. So two binary string, and then the other one dot two binary string, and they're not going to line properly, are they? That's not telling me anything. Bob, you got to see to get day 1 again. Disassembling the orb rooms? Yes, I'm disassembling them. In particular, I walked from the room 22 to the minus room. Once while holding the orb, once while not holding the orb, and I found a function that was called in one case and not in the other, and that is this function here. And this looks to be a subtraction function. So you can see how it's doing subtraction. You can see it checking for overflow. I don't understand exactly how it's doing subtraction yet, but I think it's subtraction. Because it is checking, I don't know, it's checking max value, and it does the addition, and it adds 1. Right? That looks like the tilde one we were doing earlier. This. And then read mem R1 the value in R2. Then we jump to 1747. Where's 1747? Okay, all right. We skip past the part where we set R1 to 0. So if we ever hit max value, we just set R1 to 0 and we go away. If R1 is max value, we set to 0. Otherwise, we add a weird number to it, add 1 plus 1. And why are we reading from memory? Ah. Okay. Okay, this is worthwhile. So we found the subtraction function. Cool. Why does it set to 0? It's like a floor subtraction or something. It won't go negative. And if that's actually how it works, then we could take advantage of that, yeah? Except it shatters. It should shatter. I just don't know where these magic number values come from. And this one appears here again. No, it's not quite the same. Maybe these aren't like, I think these are constants. Otherwise, they would show up as R1 and R2 or whatever. I don't, I can't dereference them because this is static. This isn't dynamic bytecode. So those are constants. And I don't know what to make of them. And you know what? We're not even doing a subtraction yet. Hold up, right? We moved from 22 to here, holding the orb. We're not even doing subtraction. Um, we're just turning on our subtraction token. Okay, well that is definitely a function of interest. Let's go back to the worksheet. And what I want to do is take one more step and actually do the subtraction. S1. And where we go, so we had to take orb and we go west. Okay, so I think here, oh, we toggled the op log before even taking the orb. I think I would have wanted to do this. Whoops. Take orb and then toggle the op log and then walk west. And now what I want to do is take one step west, and then now we turn on the op log and take another step west. Okay, so here we're logging just one step west. Yeah, I should have noticed that earlier. And what is the difference between these two? It is literally the same number of instructions in both cases, even though one has the orb and one doesn't. Why? Hmm. Why? um, they should have drastically different states, yeah? Maybe it just runs the math no matter what. Well, I mean, they should be saying different things too. Right, what we could do here We could take these two, and we could see what it says after each of these. So we could do this by taking that output q dot dq. Yeah. Okay, this is how we can confirm that. Those two should have different messages. I don't understand. Try help for instructions. Oh. Oh, okay. Yeah, that's why they're identical. Okay, fair enough, fair enough. Um, so what's going on here? We take orb, we walk west, we walk west. Surely. Um, that's a better outcome than it actually being identical. Um, I guess we have to say go west. Do we? I thought we didn't have to say go. I haven't been saying go. Go west and then go west. And okay, well, we're typing this into all of these. Oh wait, it's gonna say I can't understand because we never removed the history log, right? So here, what's gonna happen? This is the last time we removed the output queue. So we only want the output queue from the last command. So before we toggle the op log, here, we remove the output queue. Clear that up. Okay, now we do that. It could be responding, I do not understand, to like something that happened a couple beats ago that wasn't synced. Because we're not forced to handle the output as it comes. Which kind of makes me want to redesign. We're still getting I don't understand. I mean, surely everything worked until here, right? So use teleporter, north, north, north. Yeah, we did all that stuff. So we go to the vault. Then we remove all our output. Let's just do this. Emu equals emu.feed look, and then emu.use. No, let's just look at our output queue. Output queue. DQ. And then emu equals. I suppose we have to progress until blocked after we look. Feed look progress until blocked. Equals emu dot use output. Yeah, make sure there's no output. And this string here should just be the look in the vault. So I want to confirm that this whole thing is running properly. Mm-hmm. It doesn't seem to be running just yet. But actually, what's going on here? It's still saying, yeah, I don't understand. And the sizes are still identical. Did we miss new lines somewhere? And are we compiling actually? Play vault worksheet. Okay, I might have to run this elsewhere. I don't know why I'm not getting, let's look at my status here. Uh, it doesn't say it's pop. It says it's still running. Okay, it's reevaluating the worksheet right now. That should open up there. Man, you see how good of a tool a worksheet would be if it always worked, right? Like, it's really nice when it works. And then when you run into these situations where it's just not like showing me my output, this one should have output, right? That line should totally have output. But also, I'm just not even sure what's wrong here. We know that this whole list works. We know it even works with a look because that's how we usually start the main. So if we look at the main in Synacor, yeah, after we do that, progress until blocked, and when we clear the output queue. Then our first thing we do is we feed look, feed multiple, progress until blocked, feed multiple, progress until blocked, feed one, progress until blocked. Right, we can feed a look there, and we should be able to, whoops, instead of looking, we should be able to just take the orb and go west. Also west, oh my fucking god. The map. We can't go west. We're here. We go east. I go east. Go east. Uh, it's too late at night. This might have to be where I do a cliffhanger. And we still haven't done the Ackerman function. Maybe we take a look at the Ackerman function, and then, that's something we can make more progress on. Okay, great. That looks more like I'm expecting. Cool. So the difference between these two, that make commands run nearly 5,000 and 3,000. Cool. And that was just the final go east. The second go east. Right, so we're walking from the subtract sign to the 9 up here. And let's see what gets called. This has double the function calls, and what's the most popular? And more importantly, what's called by 1 that's not called by 2? There's several of them actually. Okay, let's do a for each print line, and let's look for each print line. Okay, this is actually something valuable. Whatever we were looking at last time wasn't as valuable, but this here, I hope, is readable enough that we can actually do something with it. Yeah, exactly. I'm gonna copy this worksheet output, or no. Well, Actually, we do want to copy this worksheet output. Scratch for, because we want those addresses. And we want to go to our play.scala, no, our play vault worksheet. Nope, nope, nope. We have too many play worksheets here. Okay. So these 4 functions. We don't want this either because we have a nicer version of this somewhere. I think it is play.scala because this is the one that we print. Okay. And while we're at it, we need to refactor this because it's getting silly to keep copy pasting this. So let's make a function called print extract. So def print extract, and we have an address. And where's this pair coming from actually for each show? Memory extract function that returns pairs. Okay. So we have an address, and this is going to be a unit. This here should return a string. String. And then now we take this bit here. Whoops. Copy in our address. Actually, we already have an address. We'll map to a show, and then we'll print line for the address. Okay. Format that properly. We want it to hex, and we show the call. And then we do this, we print line that as well. Map show for each print line. There we go. Now all of these can be print extract, something like that. We can take out these. Yeah, let's just do big multi-line edit. Did you miss the Bluetooth Rubik's Cubes? No, you did not. I've not pulled those out yet, but I should someday. And we can just do that. Actually, we could just do that to address, right? Oh, hold up. We've got this return in there. So there's another method. Okay, so we can leave that alone. And then the for each show can just disappear from all of those. Okay, and we do something similar to these down here. 1, 2, 3. Oh, that R3 is not going to be helpful. So we're going to do it 4 times, right? 1, 2, 3, 4. Print extract that to address. Uh, yeah, and these are all from -9 or something. Yeah, volt. And right, this needs a return value to pass. Ret int equals, we'll default that to 0, and then we'll pass it on here in extract function. Ret equals ret. Okay. So we'll run Synacor.play, and we'll look at those new functions. Oh, it seemed to be fine with whatever that was. Cool. We need an extra new line in there. So let's just throw in an extra print line afterwards. Alrighty. Do I even have one right? I usually have one right next to me, but I don't today. Oh no, I'm lying. I'm lying. I do have one. So I used to be really into these as a high schooler back in the day, and I'm okay. I'm not fast. I'm not. Well, I'm faster than average, but I'm not like you know, the kids these days. The kids these days are real fast. Um. Anyway, I once gave a talk on a Rubik's cube and group theory. So you can solve this with just group theory. And it was at a Scala conference. So I did um a combination of functional programming and group theory, uh, and how to like solve the Rubik's cube, actually solve it. Um, and then the pandemic happened, and I gave my talk remotely. So I bought a Bluetooth Rubik's cube, and I connected it to my screen, and I was able to use that for demos. And it was pretty fun. So I did live demos of like, here's a permutation, here's how here's how you multiply permutations and stuff like that. And the whole point of the talk was basically um, using theory to make a problem more approachable. So my goal is to let people know, like, hey, actually, this thing is pretty solvable. Well, not just like look it up on YouTube solvable, but like you can figure out how to solve it, and you can simplify it to the point where like you can teach a computer to solve it here. There's just a few principles, and they can guide you here. And it turns out like the group type class works out really well, and I was able to use it to make a nice little DSL. So it's like nice, just combining all of the FP things and the math things. Yeah. Um, that's actually part of why I got into uh why I started streaming. I gave talks, and I'm not the best at giving a prepared talk. Like I freeze up, I speak too fast, I get nervous, all that stuff. So part of the idea with doing stuff on the computer was to um practice speaking live and doing live coding and all that. And I basically was like, hey, you know what? My Rubik's Cube talk wasn't as good as I wanted it to be. I should do like a live recording and do like a screencast version of it. And it turns out that's really hard. So part of live streaming is practice for giving talks. But now that I've been doing live streaming, I don't like care as much about talks. I uh I much prefer just live streaming to doing talks at all. Yeah. So my hope is that this is somewhat approachable. Let's see, where's the link here? But the thing is, I'm packing a lot into half an hour. Um, so you'd probably have to like slow it down and look at it bit by bit. But like all the concepts are there, right? Like it has everything you need in order to like go home and take this out and like struggle on it for a week and figure out for yourself. So here's that link. You've been trying to, yeah. But instant insanity was one of the first physical puzzles to expose you to the magic of graph theory. Really open your mind. Oh, cool, cool. I'd say group theory is actually pretty approachable as far as like math fields go. um, yeah, I still want to make like the better version of that. Again, I'm not the best I'm not the best speaker, but I packed good info, and I think it still links to the GitHub repo, and that should be useful. Oh no, you know what? Let me pull up the GitHub repo while we're here. Stu squared twisty oops, or I just GitHub twisty oops. Okay, so here's like the companion GitHub repo for that project. Yeah, absolutely. And this is one of the things I've been wanting to do on stream is like revisit this project. It's been years since I've done it. But I want to like have it connected to my own. I've been meaning to relearn like blindfold solving, and I want to make a panel that can track all of the states for me, like basically a trainer for blindfolded solving. Um, and this would be like the perfect base for doing that. So one of these days, I'll work on some side projects using the Bluetooth cube, and then we can do some demos and stuff like that. It'd be pretty fun. Um, yeah. Now where are we here? I think it's probably getting pretty close to time to wrap up. Um, we just need to show these, right? Let's pull those the from the REPL. So these last four calls. Oh boy, that one there is a big one. We need to understand those. Um, gee, that one's gnarly. Okay, so this is stuff I might save for next time. And I know I kept saying we will do the Ackermann function tonight, but I might just have to start with the Ackermann function next time, because I think that will be a lot more approachable than this. Yeah, absolutely. And if you're not already in Discord, that's probably the best way. I don't know who else is in here, but that's the best way to keep track of my future projects. And as far as scheduling, I'm not gonna be able to finish this tomorrow night or the next night. In fact, I'm not entirely sure what my schedule will be like post Christmas. So I'll figure that out, and I'll put it on Discord, and I'll be sure to update my Twitch and YouTube schedules as well. Um, just try and keep things a lot more up to date there, because I do want to finish this project, but you know, we're obviously not going to get there tonight. Um, yeah, but you know what? It'll give me time to like sit and dwell on this. So, what are the things that we want to sit and dwell on before the next time? And maybe, maybe Bad Cop or Dave Eddy will be on doing this. So, what did we accomplish today? Let's see. We explored the vault. Um, tried Dijkstra. Did I spell that right? Tried Dijkstra to find solution. Um, probably need to use math. Mm, yeah, a Dijkstra isn't working. Uh, the overflow problem extracted -9 bytecode for functions of interest. DIJK. Dijkstra. There we go. Um, sorry, that -9 bytecode. And then what else did we extract? I think we've realized that, it'd be nicer. I might want to give myself more tooling. There are like little things I mention every now and then. Oh, it'd be nice to have a save state, or oh, it'd be nice to be able to diff, I don't know, this or that. Um, but maybe tooling is a little bit of a distraction, and maybe I need to, maybe I already have what I need in front of me, and I just need to solve it. Uh, Still need to actually Dijkstra. Still need to, not Dijkstra, to reverse the Ackermann function. And that's what we have to look forward to next time. So this thread here, and these functions of interest, and the vault solution itself. Those are potentially 3 big problems. Uh, wow. I thought like this one might be easier, but maybe I'll sleep on that and I'll realize, oh, it's a lot easier than I'm making it. And I suppose the reason I'm doing this overflow, the reason I'm even checking for this -9 is to see what happens with the overflow. So maybe this is the first thing we should do. First thing we'll do is look back at that, see how overflow is handled, and then go back to fixing our search. Or maybe that's a distracting side quest, and it's more straightforward than I thought there. It is still interesting. Every time you like dig into a function to like try and disassemble it. Um, but yeah, I can't imagine actually writing a proper decompiler, not without knowing how it's actually compiled and knowing that follows certain rules for it to output. But anyway, this was fun. So I'll probably still have some sort of schedule in the same time slot. We'll see what we can sneak in. I'll keep everyone posted on. Yeah, I'd be writing a disassembler totally, and I'll keep everyone posted on Discord. And of course, I'll update my YouTube and Twitch schedules. My schedules, I set them to 15 minutes before midnight so that the day is not confusing. But I actually mean midnight by that. Maybe I'll set it to like 1 minute before midnight. Um, Let us find a raid. See you next December. I'm not going anywhere this time. Yeah, no, thanks for being around. Absolutely. It's been a great Advent season. I think this has been my funnest Advent season. I mean, well, because of Synacor, but just um, it's been a good time for sure. And I like how much more relaxed it's been. Synacor. Oh, Bad Cop is still doing Synacor. So we go finish on Bad Cop. Yeah, have a great Christmas, you too. And I won't leave you after Christmas. Alrighty. Raid Bad Cop. Hmm. It's been a pleasure. Oh, I think I am still streaming.